We will discuss now a important thing. It is a property P of a string said to be number 1 decidable, number 2 semi-decidable, and number 3 is undecidable. So we will study these three things. That is, a property P is said to be decidable when it is decidable. Next, semi-decidable when this is semi-decidable, and when it is undecidable. Okay. So to begin with, let us first consider one thing, that there is one property P. Okay, and what is this property? It is a property is a string with WW forms. Okay, means suppose a string is like this way, AB. So AB is W and this AB is W. So this is a property of WW forms. And what we will do, we will take a bag. Imagine we are taking a bag, and we will check all the strings, okay, which satisfy this condition, WW condition. Suppose first we check one string, suppose x1 is satisfy this condition, this property. So I put in this bag. Similarly, I will take a next string. It is also satisfying this WW condition. I am put this bag. Suppose x3 is another such kind of string, and so this we are putting this kind of n number of strings which is satisfying this property, that is WW property, and we keep on putting into the bags. Okay. Now what is this x1, x2, x3? Upon keeping all this x1, x2, x3 into the bag, basically this is forming nothing but a language. Okay. So property and language, basically you can understand. So property which satisfy WW, this is the property, and the string which is satisfying this property, ultimately that set of those all strings are forming a language. So this is some, you can say that the relation between property and language. Okay. Now from this we have to decide what is decidable and what is undecidable. Okay. So let us first design a Turing machine, total Turing machine. Already we have discussed about the total Turing machine. So let us design one total Turing machine. So it is a total Turing machine. Okay, so I represent is as TTM. Okay, so what I am going to do, this is a total Turing machine, and suppose this Turing machine is accepting this some languages. Okay. And this language is accepted, then it is decidable. So what we can say that collecting all these strings. So first I am deciding, I am writing about decidable problems. Okay. So as a definition, you can say that collecting all strings, collecting all the strings, collecting all the strings which have a property, which have a property, collecting all the strings which have a property, and all the string form a language. Okay. And if that language is accepted by total Turing machine, okay, then that language is said to be decidable. is said to be decidable. So what is decidable language? First of all, you have to satisfy some property and make a language, okay? And if that these all languages is accepted by total Turing machine, okay? It is total Turing machine, not Turing machine. It is total Turing machine. So if those languages are accepted by total Turing machine, then that language is said to be decidable, okay? So this is the normal definition of decidable language, okay? Now let us consider what is semi-decidable language, okay? So number 2 is semi-decidable. So it is nothing but, suppose you take, in this case you take a Turing machine, not total Turing machine, okay? So in case of semi-decidable, it will be a Turing machine and the language may be accepted, may be rejected, or it may loop, because Turing machine has these three properties. Either it may accept the language, or it may reject the language, or it may loop, whereas total Turing machine has only two properties, that is either it can accept or it can reject. So we can say that it is the semi-decidable means that it will be a Turing machine and the language may be accepted, rejected, or it may loop, okay? So in case of decidable there we will just imagine it will be a total Turing machine and the language will be accepted or rejected by the total Turing machine. In case of semi-decidable, it will be only Turing machine, so the language may be accepted, may be rejected, or may be looped, so it is semi-decidable. And number 3 point, as you know, that is undecidable. So what is undecidable? If there is no Turing machine for the language, okay, so we can write that if there is no Turing machine for the language, then it is called undecidable, okay? So we have come to the conclusion that when the language will be accepted or rejected by total Turing machine, it is called decidable. When the language may be accepted, may be rejected, or may be looped by Turing machine, then it is called semi-decidable. And the language which is not accepted by total Turing machine, okay, not Turing machine, but it is total Turing machine. So if there is no total, I have forgotten. So if there is no total Turing machine for the language, then it is called undecidable. So these things are very important. So hope you understand this. Okay, thank you. Next we will understand what is universal Turing machine. Universal Turing machine. So before discussing what, we will first understand what it is Turing machine encoding. Turing machine encoding. Okay, so 0 to, because Turing machine you can represent in binary format. Everything can be represented in binary format because computer only accepted binary format. So it is noteworthy that you should know it. Okay, so this is some binary format. Okay, now let us represent for the Turing machine. What are the specialties of Turing machine? So first there will be some input symbols. Okay, next there are some states. Okay, so this is the starting state, this is the reject state, this T represents some final state. Okay, and suppose let us say Q, this represents any other state. So this is the starting state. Okay, this is the reject state, this is the final state, and Q represent any of the states. So these four combinations are nothing but states. Okay, now there will be some tape symbols. Let us consider this A, B, X, Y. I have taken these 4 tape symbols. Okay, so these are tape symbols. Apart from this, there are many symbols are there, like these symbols, and there are many symbols, so we will not consider those. We will just consider some main important parts. Okay, now next what we will do, that we will represent this S by 0, R by 1, T by 2, and Q by 3. Okay, E, we will represent A by A0, B equal to 1, AB, X is equal to 2, and Y equal to 3. Okay, and also, you know, in case of Turing machine, there is a left movement and right movement. So let us consider we will represent left shift by L1 and right shift by suppose 2. Okay, you can take any numbers, but I represent in this format. Okay, so what we can say, that since by saying this we can represent these things by this way. See, 0. Okay, how many number of states are there? So if I say 4, so we will represent these states by like this way. Okay, 0 to the power 4. How many types are there? So we can represent this 4 by types, because this 4 means there are 4 number of states. Now this can I will discuss just afterwards, giving a problem. 4 means this is, let us consider this a tape symbol, so this can represent a tape symbols. So also there are 2 input numbers, so we will represent by this two input numbers. Okay, now let us consider another thing about a particular transition. Suppose this given, there is a transition SA and it comes to QBR. Okay, so next it is Q, replacing A by B, and shift is right. So how we could represent this? Now see, we could represent like this way. So this S, so we will write 0 to the power S. Okay, then A, this one, so 0 to the power A. Okay, next Q, 0 to the power Q. Next this B, so I will write 0 to the power B and 0 to the power R. So we can write this way. Now we will do it is binary encoding. Okay, we are already given these numbers, what do you mean by S, what is R, what is B, and etc. So for the binary encoding, let us see how it is done. So let us write binary encoding. Okay, so in binary encoding format, we will write what? 0 to the, now S is what? S is nothing but it is 0. So we will write 0 to the power 0. 0 to the power A is what? A is also 0. So 0 to the power 0. Now what is Q? 0, it is 3, I think. Yes, it is 3. What is B? B is, I think, 1. So it is 1. And what is R? R is 2. So 0 to the power 2. So this is a binary encoding of this particular transition ID. Okay. So you have to remember this, all the things, and this way basically the thing is accepted by the Turing machines. Okay, so in the next part, or in the next lecture, we will discuss about the universal Turing machine. Okay, so let us concentrate on basically we're starting universal Turing machine, but we will go in depth of universal Turing machine in the next part. Okay.